Okay, hello everyone to the chemistry talk of this year. The speaker is Sayantan Chakraborty, who is coming here from Singapore. And his research area is on quantum computing. He was a student here until last year and is now postdoc in Affiliation.
So this was in no way, shape, or plan at all. And basically, what happened was Piyush and I got out talking yesterday. And I told him that I'm in Mumbai. He asked me to give a talk, and unfortunately, here we are. But let's see. So if it's a little janky, please feel free to interrupt me and ask questions. So this work is an offshoot of something that was presented at ISIT earlier this year with another set of authors with only count. But we feel this is like the most pristine version of this problem. Okay. So before going to the next slide, and before going any kind of what is this problem about? It's a very cute little thing. It's not useful at all in any way, but there. So we sort of know what quantum states are. Okay, they are some kind of physical resource, some kind of physical object which you can make up in a lab. But often these quantum states are mixed. They are noisy in the sense that mathematically quantum states on some register are described as a positive semi-definite matrix with some sort of eigen decomposition like this. Is everybody familiar with this notation? More or less. Okay, not familiar. So this is the vector. Okay, this is basically a column vector, and this is a row vector. Okay, but this vector is on this register. So if you think of vectors as functions from some finite set A to the reals, or in this case to the complexes, then you have this guy. Okay. So this notation is basically the Chakraborty notation for those who know. Yeah, so in general, quantum states look like this, and as you can see, this very much looks like a probability distribution. Okay, you forget about this part, it looks pretty much the same as if I had only written this blah blah blah. But the difference here is that this object actually physically exists, and these guys represent some orthogonal directions, or rather one-dimensional subspaces. Okay, so this is in general what a quantum state is. Now, when we actually create quantum circuits in the lab, let's say I want to make a quantum circuit, very often a resource that we take for granted are pure states. That is what computer science is known as workspace. Okay. So you might have some sort of circuit with some inputs, yeah. And along with this, you just extend this. This is not really doing anything, but you provide some extra stuff. And that extra stuff in quantum is provided as a pure state written as just K0, but this K0 might not be a single qubit. It might be multiple qubits, K0 tensor, K0 tensor, K0. Okay. So this is your usual workspace. And this is pretty much taken for granted. The question we are asking here is, given any kind of this noisy general quantum state, can you get a pure state back? That is there a general recipe for turning any noisy quantum state back to this pure state? Okay, so by pure state, do you mean that when the distribution is a point distribution? Yes, exactly. So by pure state, I mean just this. And the coefficient here is 1. I mean, you can put any kind of thing here, but we will adopt this notation. Okay. And I usually use this Chakraborty notation and not the vector notation because that makes things a little easier for us. So, yeah. So first of all, why is this not a bullshit question? Anybody who knows a little bit of linear algebra will immediately tell you that, okay, so first of all, what kind of operations am I even allowing? So if you want to recover pure states, you can't really provide pure states at the beginning. That makes no sense. So in quantum, if you're not providing any workspace to begin with, you only allow your circuits can only do local unitary operations. Okay. So at least for now, let us concentrate on local unitary operations. But as you can see, this object is a matrix. This is a matrix of some non-trivial rank maybe much greater than 1. And unitary operations preserve rank. So how the hell do you expect to get a rank 1 object from a non-rank 1 object using unitary matrices? So that's where the formulation of the problem really comes. Actually, the problem has 2 parts, but I want to go a little slowly. Okay, so this is problem part 1. This is called the local period distribution problem. Where given any quantum state on some system A, which we call rho effect, can you design a circuit or otherwise a unitary operator U on A to an isomorphic system APAG? Now, what is this? So A is isomorphic to AP tensor H. So these are 2 vector spaces, and this is my notation for the whole thing. Okay. Such that when you do that unitary on A and then simply discard H, that trace out operation, in terms of if you think in terms of probability distributions, that trace out operation is simply marginalization. So if you have like a joint distribution Pxy, you're marginalizing Y. That is the same as this trace out operation. Just think of it that way. You throw away this AG part. Whatever you're left with on the AP system should be close in some sense, in some norm, to a pure state. This is our requirement. This is part of the problem 1. Actually, this is very easy to do. Let's see how. And this is entirely going to be proved by picture. So, okay. So forget quantum, forget all this complicated business. What is rho? Rho is a probability distribution. Okay. And since it's a positive semi-definite matrix, these guys are all greater than or equal to 0 and they add up to 1. So basically it's a probability distribution, as I said earlier. Technically we call them eigenvalues because as you can see, those are what I wrote is an eigendecomposition of a matrix. Okay. But let's think of it in terms of probability distributions. So what we have here is the eigendecomposition of this state rho written in ascending order. Okay. So these are its eigenvalues lambda 1, lambda 2 up till lambda max ascending order. Now what I'm going to do is I'm going to perturb this guy and remember this whole thing is on the whole space A. There are maybe as many as 8 dimensions, but some of these guys might even be 0. I don't really care. This whole stretch is covering the entire vector space A. Okay. So first, why are these guys red? They are basically the smallest eigenvalues which add up to my error parameter epsilon. And remember this, where did this epsilon show up? Where did this epsilon show up? It's my allowable error to how close I can get to this velocity. Okay, that's where that epsilon comes from. Okay. So these red guys are basically the smallest eigenvalues, all of which add up to epsilon. Great. So now I'm going to do a perturbation by simply throwing them away. What I have left is not a probability distribution, it's a sub-distribution. Okay, so that's why I call it rho prime. But in the 1 norm, or in terms of probability distribution, total variation distance, or whatever you call it, this thing is epsilon close to your original probability distribution rho. That's very clear, right? But now I have my recipe. What am I going to do? See, now this entire part is empty. So what I can do is I can divide this whole thing into blocks, each of size whatever this green part is occupied. And I can label each of those blocks with some number. Yeah. For the sake of it, for now, let me define this complicated looking thing. Some of you might have heard some H max entropy, mil entropy. Forget how complicated it is. It's just some quantity form. It's my definition. Okay. So the definition of this quantity is just that you do this operation that I just did, throw away the smallest eigenvalue which add up to epsilon, whatever is left, take the log of that That will be your definition for this guy. I'll just call it H max epsilon. Forget the data. But this whole thing is of size A. What is the dimension? And I divide this whole guy into A divided by this 2 to the H max number of labels. Okay? Fair enough? This is just a relabeling. It's a renaming of the entire space. And so this relabeling is what? It's a unitary operation. So what did I just do? What I just did was the following. I divided the entire vector space A into blocks, where each block is of size of A divided by 2 to the H max epsilon, whatever. Okay. And what is the renaming operation? If there was a vector in this vector space, let's say some get I, I'm going to rename this guy into its block index and the index inside the block. So block index tensored with index inside. And notice that very cleverly, or not so much, I have the block index of the non-zero eigenvalues is 0. And this operation is unitary. Relabeling is a unitary operation. So think of it in terms of permutations. Okay? And that's it.
Why does that become 0? Like, that is just the index, right? 0, 1, 2.
So I have artificially set it as 0. So suppose that you are like 1 say 32. Okay. You divide that into groups of, let's say, 4. Okay. So 8, 8, 8, 8 like that. So you have block index, 0 is block, first block, second block, third block, fourth block, and you have a guy inside going from 1 to 8. Okay. Okay. So, and this relabeling operation again, it's a unitary operation. I'm just relabeling the vectors of the entire vector space. So when that unitary acts on this substate, what you are left with is this label 0, Ketbra 0. So let me actually explicitly do that calculation.
And maybe a silly question, but like, this dropping off, what have you first dropped?
I'll come into that. I answered it because. So what just happened is there are some of these vectors living in the vector space. I acted the unitary order. Now, see, why am I doing this on both sides? That does everybody know why I just did this? Okay, everybody doesn't know. Basically, general quantum operations, any general quantum operation, take this as an axiom. Okay, any general quantum operation consists of only 2 things. You have some system A, you can put in some extra workspace. So general quantum operation on this thing would, let's say the workspace is W, would be unitary on AW. You need a dagger on AW. Why do we need the dagger? Because we want quantum operations to be positive certain. Then you want to map positive certain operators to positive certain. And if you don't have this conjugate structure, that's not going to happen in general. Followed by a trace out on the double system. So any quantum operation, any operation in nature that is we call quantum can be captured by this. Okay. That's just axiom. I mean, it can go for deeper, but that's not what we're talking about. So anyway, what exactly did my relabeling operation do? So remember we had rho. It was EA, Kedbra A. After I did U rho U dagger, where the U is the relabeling operation. Okay. What happened was, for now I assume that I okay, maybe rho. Sorry. So this is not a state, this is substate. I've thrown away some of the smaller guys. Okay. This becomes A prime on the inside the block. So this A prime is the index inside the block tensored with the block index 0. Is this clear to everyone? Great. And after that, I'm going to trace out this part. What I'm left with is the vector. So what the hell did I just do? How did I pull out pure states from a mixed state? What we did was we gathered all the highest, the largest eigenvalues together, the largest subspace of this thing, which has most of the mass. Okay, I pushed it to one side and I divided the whole space into blocks and I just relabeled things. That's all I did. Now, coming to your question, how does this relate to the original thing? So this works very well when I have thrown away those small eigenvalues, blah blah blah. So it works extremely well. But when you actually have non-zero guys sitting here, what the hell happens? What happens is you can use the monotonicity of the one norm. So the one norm between two probability distributions does not increase under permutations. In more generality, it does not increase under the action of unitary operators. So what you did just now was a unitary operation. So more precisely, we have the original row. I threw away some things and I got a row back. Think of this as total variation. And we know that this is true. This metric does not increase under the action of unitaries, permutations, and things like that. So if I put a unitary on both of these guys, the distance is not going to increase. So that means that is implies but now I can write. Remember what this looked like. Some junk tensored with frequency. Fair enough? But now I have one more step to do. I have to throw things away. And the one norm is nice enough that even under throwing things away, the distance never increases. And this is intuitively very, very obvious. If you have two very long vectors and you take the distance between them, you take the one norm between them, you are literally comparing index to index. So if you throw away some subset of indices, your distance can never increase. So once you do the trace out operation, tracing out of the junk part, notation is AG because of historical reasons. I would have called it junk, but whatever. It's trace out of this whole thing. Now, what does trace out do? It simply erases the junk. It turns it into a scalar, one. That's it. And this is actually very easy. This is almost trivial. Okay? Great. As it turns out, everybody's clear so far? More or less?
What is the restriction on the dimensions of the
Only bounded. It needs to be only bounded. That's it.
No, why don't I have AGB the trivial space? So then I don't have to do anything about
That depends on your state now. So the thing that is like you provide me a row, and then I can design my AP and AGB.
No, but I can design AP to be everything, so I don't have to do anything. Everything will be junk.
No, but you have to preserve this distance, right? You have to retain.
Yeah, it will be the same distribution. So any vector space I can write it as the null space tensor with the same space.
I don't understand the question.
Then you go back to the theorem.
Sure.
Yeah, so what I'm saying is that if AP is the null is the trivial space,
What is it?
just the zero, the set zero.
Just
Dimension zero.
So you want to make AP as large as possible. And you can obviously declare it to be trivial.
Exactly, that's what I'm saying.
Okay, I understand the question. Yeah. So the point is that you want to get the point of this whole exercise is that you want to get as much you want to make AP as large as possible, right? That's the whole point. Maybe I should have said this earlier. So obviously you can set it to be something very small or completely trivial. That's a trivial solution. But the question is how large can I make AP? Yeah. And that's where all this business comes in. So actually, how large of an API did I get? So remember, the dimension of the whole space was A, and the size of each block was this business. So each AP is of size this. So when I take the log, and we like working in logs because we can literally count that qubits are in the log space. We count qubits in the log space. So log of this AP is log size of A minus H max. And this is actually the statement of the day of this theorem. Yeah. This is the statement of this. That using this construction that I just showed, you can get a pure component out of the state that you had as input, which is at least as large as this much. Okay? Can we do better? It does not work. There's an upper bound. You can very easily prove an upper bound to this, and it's not very interesting. Now this is old. So now let me get into a little history for this problem. So this is the easy part of the problem, what I explained till now. The really interesting stuff comes later. I don't know whether I can get to the whole picture, but this line of work was started by Devertak in 2005. And in fact, even earlier than that, when people were first starting to really play around with entanglement and all of the pure states, blah, 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 all of these things. And what can you do when you're not thinking about how complex your operations are? Just can you show existential arguments? That's when all of this business started. But this original paper is pretty horrible, this one. So it took me at least a month or 2 months to sort of understand it. What you see is the crystallization of that understanding using modern CS kind of thinking, algorithmic kind of thinking. You talk to, okay, maybe I shouldn't say this, but you talk to a traditional information theory guy, he's not going to like this. This is very CS style of stuff, okay? Oh. Now let me get to the really interesting stuff. This problem can be generalized in the following way. Suppose now that instead of this local, why did I call it loop? Because let's say I have a lab and I have the state in that lab, and I'm doing this whole business in that lab. There is no party somewhere else or anything like that. But suppose now that there are actually two parts. I want to make a distributed knowledge. So what would be a sensible distributed generalization? So one way to do it is, let's say that we have a bipartite state rho AP where the A system is accessible to Alice, and Alice can do operations on the A system. And Bob can do operations on the B system. But they are not allowed to do joint operations on it. So any quantum operation that is done has to be something on A, let's say something, let me write this very informally, something on A, tensored something on B. You cannot have joint operations. That is, you cannot, let's say, for example, full unitary on AP, this sort of thing is not about. Okay. This is usual distributed generalization. But is it interesting? Just don't look at the next ones. Just this is very interesting. So trivial solution is the following. What we saw previously is a locally optimal, right? Upper and lower bounds almost match. So Alice can do a locally optimal thing. She will get log dimension A minus H max. Bob can do a locally optimal thing. She will get log dimension B minus H max. You add these two up, you get some amount of period. The question is, can we do better? And without anything else, without any more, I mean, if I don't allow, let's say, communication or shared randomness or something like that, without any of these extra resources, this is pretty much the best you can. It's not very hard to see. So what we can make this problem more interesting by allowing communication. Now, this actually raises more questions than it solves. When I allow communication, what kind of communication do I allow? Do I allow classical communication? Do I have quantum communication? Then these things are actually different. Mathematically, they're very different. When I say quantum communication, I mean I am allowed to send quantum states through some kind of channel. When I say classical communication, I mean I'm allowed to send bits through some kind of channel, not qubits. So entanglement is not, these are all sorts of things. So suppose I give you the full power, that I give you a completely noiseless quantum channel from A to B. What does that mean? That means that Alice can take a ray, push it through an identity operator acting on A to B. Let's say one of these systems is bigger, but you can always embed it into an equidistant system. So the identity operator from A to B and basically send this whole thing to Bob. So now Bob has the entire state to it. And again, he can do a full joint operation. Now it's local for him. So he can do a full joint operation on the entire AB system. And he's done. So again, not interesting. So what is a reasonable generalization where things are not trivial, but also like somewhat challenging? That, it turns out, is the case when we allow classical communication. Okay. But again, suppose I allow classical communication. Are things interesting? Can we do something better than what I would have gotten if I did two separate locally optimal protocols? Here's some evidence that is actually true. So I'll get to this stuff later. Yeah. So consider this state. Okay. All of you will recognize this as a maximally correlated state or shared randomness on two bits. Okay. So if Alice has 0, Bob has 0. If Alice has 1, Bob has 1. This is a classical state. Okay, there is no entanglement, nothing. This is simply this distribution. This joint distribution. Okay. So anyway, yeah. Now, notice that suppose Alice does the locally optimal on her A system. Okay. What does the locally optimal on the A system look like? So, how do we even picture it? So forget the system B. Trace out kar. Just throw it out and do the locally optimal system. The distribution of system A is a uniform distribution on 2 bits. This is Bernoulli half. Okay. So you can't do all that eigenvalue shifting, epsilon mass shifting business at all. For small enough epsilon, you can't throw away anything. So the amount of purity that you will get out, the pure stuff that you can get out is nothing. And you can see that in this calculation. That the end, this H max in that case is 1, is a log of the size of the entire thing. But the entire space is also log 2. So the amount of purity you get out is 0. You get nothing. Absolutely symmetrical argument for Bob. He gets nothing. So if you do 2 local protocols without any kind of communication, anything, nothing, you basically get no purity. Hands on. But now let's say I allow classical communication from Alice to Bob. And when I say classical communication, no one is going. So when we talk in terms of quantum channels, a classical communication channel is usually called a completely dephasing channel. What that means is the channel measures in the computational basis and sends with some probability that symbol, that classical symbol in the computational basis. It's defined like this. So this is the channel T from X Alice to X Bob. If it is acting on a state node, what this channel is going to do is let's fix the basis first for state on the A system. Fix the computational basis for this A system. Computational means the canonical basis. Okay. So this channel is going to do a measurement along the subspace and just send this symbol to Bob. So as you can see, this is an inner product. Is everybody familiar with this notation? Yeah, no, this is fine. So this is just paste. You're projecting rho along this one dimensional subspace. This is a number greater than or equal to 0. All of these numbers add up to 1, so indeed it's probability distribution. Okay. And with this probability, you send the classical symbol x, because see, x we have fixed to be in the computation. This is the classical symbol x to Bob. So this is a classical, this is exactly what a classical channel does. You give it, so suppose that rho was a distribution, rho was already written in the computations. What would this operation be? If rho was summation x get graph x, and I did this number would turn out to be precisely px. So what is happening here is that you pick x with probability px, and that is exactly what you send to Bob. In other words, this is the noiseless classification. Now, I have written it a little more generally because we have to define it to be able to take as input any general quantity. But in general, this is a noiseless classification, as you can see. Okay. So we apply the noiseless classical channel to it. So what will that channel do? It will do nothing. It will simply send 0 and 1 to Bob as it is. And now comes the interesting part. Bob has this entire thing. Right? And we have not done any kind of quantum communication, this entire classical communication. And Bob can do this controlled unity. So what is this controlled unity doing? If the symbol on the A system is 0, do nothing. If the symbol on the A system is 1, flip B. This is the flip operator. And what does this get us? Yeah. So we have right 0 plus 1 tensor polygons. So if your input is 0 tensor 0, this guy does nothing. It's just these are orthogonal. So it'll hit each other, disappear. Only this part stays. And it's an identity. So what you get out is Kedra 0 tensor Kedra 0. On the other hand, if your input was 1, 1, this part doesn't, disappears. This part hits 1, says that okay, 1 is there. But now I have to flip this guy. This is a flip operator. So what you get out is Kedra 0 tensor Kedra 1 tensor Kedra 0. So the total state you have after you add all these things, these are linear operators, so you can put scalars in front, add it up, it's all going to go inside. What you get is Kedra 0 tensor Kedra 0 plus Kedra 1 tensor Kedra 0. And this Kedra 0 is your unity. So you have one qubit of unity, which is strictly better than what you would have gotten if you did the locally optimal protocols. So this is some evidence that with classical communication you can indeed do better. Now, what is the lesson from here? What is the general theme here? The general theme is that we used correlations, classical correlations between Alice's system and Bob's system to get more. So here's a conjecture, which is true, it's not the conjecture is pure, but whatever. in the lecture. What I actually got here in general. This is what you were getting from the local organizations. They got something extra. That extra will be a mutual information like that. Where did this extra come? There was no X before. But then it is what is this extra? I'm looking at slightly ahead. But this additive term basically comes from the classical correlation that I was talking about this. No, I mean XP.
What is it?
Yeah, got it.
Where did A go?
Huh?
Where did A go? No, but it has to be symmetric, right? Whatever you have.
No, not really. This expression, it does not have to be symmetric. And
Bob can't send anything to us.
no. You are only allow one-way communication.
Oh, okay, let me-
Two-way communication is open, I think. I mean, if it can get into better with two-way communication, so you only have one-way communication. The point is that the lesson that we saw from the previous example is that somehow you have to use the classical correlation between A and B. But what does that even mean? Mathematically, what does that mean? Algorithmically, what does it mean? Because A is a quantum system, B is a quantum system. How do you get out classical correlations from these systems? The answer to that, and we'll see, classical correlations are captured by mutual information. Forget the max epsilon, whatever. This is the mutual information. Think of it as the good old Shannon mutual information. The answer to that is basically you have to turn that system A, you have to do something to it so that it turns classical. And now that something is a measurement. You have to measure it using some kind of measurement, some operators of us or something. Okay. Because this is exactly the hard part. And this is where I think I'll go back to one of the original slides. See, to do a measurement. Okay. Does anybody know what a measurement is? How you describe it? Nah. Remember, earlier I had said that any quantum operation, any general quantum operation can be described by a big unitary on some extended space along with tracing out of the workspace. For measurements, one of the kinds of operations that you can capture in this picture are measurements. So what are these guys? These guys are a bunch of projections. Let's say for now, let's stick to projectors. Pi 1, pi 2, say pi. These are all projectors. And they have the property that all of these guys add up to the identity of the operator on the system on which they live. How do you apply it as a quantum operation? So your system rho, your state rho A, and the measurement M is a quantum operation. And then apply this quantum operation on rho, the following thing will happen. I'll get to the general picture later, but let me explain physically what this means first. What this means is the following. You sampled rho, it's like think in terms of probability distributions. Let's say these are one-dimensional projects, okay, Kedra X kind of business, Kedra 0, Kedra 1, Kedra 2, blah, blah, blah. And this rho is again summation, some probability distribution, Kedra I. So, what is this? These are some Kedra I, right? This is some Kedra I, and this is also some Kedra I. So, what is happening here is that what this operation is doing is it's sampling from this distribution. It's sampling from this distribution and recording the sample in another register. Okay, that is precisely what this is. So this is what that X register is. This all is still happening. This is not destroyed. It is still very much there. But what the operation did is it sampled rho along some basis and recorded the outcome, recorded this index in some tape. Okay,
So the entanglement is one.
entirely one. These are entanglement destroying operations. Your entanglement is gone. But how do we describe this in the general order?
So if it was not I, it was something that two dimensions would entanglement with the pairs.
So entanglement between what and what? So if you had, let's say, A and B, but your measurement is acting only on A, then after measurement, you would have something on the B system, but you would have to trace out the A part. So what you have left then, in general, in that case, is a state like this. And this rho I is this guy on AB, but the A system traced out. And see, this is a classical quantum state. There is no entanglement here. This is not an entanglement state in general. And this is precisely what I meant when I said exploit the classical correlations. So after you do the measurement, you get a CPU state like this, and the correlation between this classical register and this quantum register is precisely what you want to utilize. But this is the looking ahead. But anyway, slide aside, can we describe measurements in this general quantum picture? Yes. And this is going to be important for the talk also. So these are some of operators, right? How do I describe it in the unitary picture? So let me define this unitary U as follows. Yeah. That's it. What the hell is this? Let's do some computations. So I'm claiming that this unitary, if you act it, or let's say isometric, okay? This isometric operator, you do the U roll U dagger business, you do the tracing out part, you will get exactly what we got earlier, what I wrote earlier. So what happens? You have actually I should right. Yeah. Technical reasons. So if I have this, this is my U, and this is my U dagger. Dagger means that adjoint.
I thought these were vectors, not any multiple vectors.
These are tensor product of two vectors.
Yeah, but one should be the other should be gone.
No. This is these are the tensor product of two vectors. So
It's a counter vector.
it's a vector. So 10 tensor product is basically like this. If you have 0, 1, and if you have AB, you say you're taking the tensor product between these. I'm doing this operation. There is a mathematical way of going to dual spaces and coming back, but that's not useful. So this thing, basically take this
0, 0, AB.
exactly 0, 0. That's what this means. Yeah, and the bra. This is U dagger, the dagger operator. Now, this is the system, this is the workspace system. What happens? I get summation ij, ij on the workspace, tensor ij on x, tensor square root pi I, rho square root pi j. And I'm going to trace this out. But see, what are the terms that survive? These are orthogonal. When I trace this, the only terms that survive are when I equal to j. So all the cross terms disappear. So when I trace this out, what I get is summation I tensor 8 square root pi I rho square root pi I. But pi's are projectors. Square root of projectors is a projector itself. This notation, this kind of extension is called the Stein-Free dilation of a measurement or an operator. Okay, this is going to be pretty important for us. I don't think I'll have enough time or whatever. But anyway, so okay, I just have 10 minutes, so I'm not going to go into too much more detail, but let me give you a broad picture of what was to come ahead for time. Yeah. So what we did essentially, was the following. We showed that there is a general recipe. So you give me any measurement. Okay. Can I using that measurement, can I get something useful out of it? Can I from this distributed state, can I get some pure states out? But it turns out this is a much harder problem than one would have bargained for. Okay. And there's some weird expressions here related to what I wrote, but whatever. And these are all one-shot expressions. But if you take what is called the asymptotic IID extension, you take multiple copies, all of those quantities are nice enough to converge to the Shannon limit, you get this. Okay, and you can work this out. This is going to be exactly log A minus HA plus log B minus HB plus I of A X colon B. So that additive extra term does appear. Okay. The hardness here is that first of all, if you give I'm saying that if you give me any measurement, can I do this? So the number of outcomes of that measurement can be very large. And on top of that, to actually be able to do a measurement on the A system, I need to be able to record the outcomes of that measurement in a separate tape register. Where the hell am I getting the register? Nobody's giving it to me for it. So that is why the original author, the 2003 author, he included point 3. That Alice in the distributed case is allowed to borrow some extra pure states from somewhere from her lab to implement her operations. But at the end of the protocol, those pure states that were borrowed have to be subtracted from the total rate. This is what we call catalytic use of pure state. This is what the catalysis comes in. It's not actually a chemistry term. I don't really like that, seriously, but Pranav really loves it. So anyway, so yeah. So this is where that catalysis business comes in. Okay. The hardness here is that you can give me this POVM business. These POVMs can be huge. I mean, they might be acting on some system A, but the number of outcomes, there is no bound on the number of outcomes. The number of outcomes might be twice the dimension of that system. So how the hell do you even then you have to implement that operation? You have to borrow twice the dimension of the system you're actually trying to get some pure states from. You're screwed. So the first theorem is that you're good, and it actually follows from some work that we did in 2022. Something called this one, something called the measurement compression theorem. It shows that if you give me any POVM, I don't really care. That POVM might have a large number of outcomes.
What is POVM?
Sorry, measurement. Sorry. You give me any measurement, it can have a very large number of outcomes. I don't give a shit. I will perturb it in some way. I will do some probabilistic magic, and I will produce another measurement with a much exponentially smaller number of outcomes, which is very much manageable for me. And I can borrow those many extra pure states to write the measurement outcomes and do something. Okay, do something. Great. This is theorem 1. But we are still not very happy. Pranav was still not very happy. That's how we actually discovered that this can be done. It turns out that, see, okay, I'm doing some probabilistic business, I'm reducing the number of outcomes so that what I have to borrow is less. The catalyst is much smaller. But it's still something. You still have to borrow some mutual information amount of catalyst, 2 to the mutual information amount of catalyst. This paper is about getting rid of that. We showed that under certain conditions, which always prevail in the asymptotic IID setting, not so much in one shot, but most of the time, you can entirely get rid of the catalyst completely. So the final result is you give me any measurement with as many number of outcomes as you want. I don't care. I'm first going to produce a measurement by some, again, probabilistic magic with a very small number of outcomes, and then I'm going to do some geometric magic to pack all of that into the A system itself. So the place where I write the outcomes of that measurement, I sort of pack it into the system A itself. And that's allowed us to get rid of the catalyst. So that's why non-catalytic. Yeah, I wish I had more time, but I only got through half of what I thought I would. But yeah, I guess, I mean, as of now, that's all I have to say, unless you guys want to stay. And I don't think that anybody wants to stay.
What is the theorem for this one?
There is this. Sure. Oh. So, given a joystick probably and some measurement on just on the system, and this measurement is provided by the form, indexed by these single text from some arbitrary class, finite class, let's say. There exists an algorithm with classical communication, of course, which can do distributed purity distillation with zero catalyst. So actually there are two conditions. There is one condition where we do need some catalyst, but so one with zero catalyst, as long as and the second part is the case when this doesn't. But I'm not going to write that because that's going to only confuse. Let's just concentrate on this. Forget the maxes and the epsilons. Just forget the maxes and the epsilons. What the hell is this? This is I x colon RB, H RB given x. This R is something. Okay? Yeah. So exactly. So this is just age of RB. Now RB, so remember we had the system AB. The state AB. R is a purifying resistor. So I am going to take a purification of this guy called ABR. Purification is I can just extend it to a single vector. Okay. That is where this R is assumption. So this, if I think in terms of channel, is HRB. And as it turns out, for pure states, HRB is exactly equal to H of A, which is always less than log H. So we basically improved the classical, the original result, which is not really something that I expected we would be able to do. I mean, I don't know many examples where one shot has been able to improve, but this is one case where we managed to do it.
Why is this an improvement?
The original paper had no control on the amount of catalyst. They didn't even consider the question of reducing the amount of catalyst. They just said you borrow as much as you want.
Okay.
Because yeah. And also this is a one-shotization, as in the original proofs are terrible. Our proofs are much clearer.
But quantitatively, it's not very good.
Quantitatively as in the amount of purity that you're getting.
Yeah.
So their results are optimal in asymptotic IIT when you have multiple copies. We get the same rates in that regime. We also get like we also get one-shot rates when you don't like finite sample rates. Okay, that's one thing. But the main improvement is that we can get the same rates but the zero band test. That's basically the point of it.
So does it imply something for their setting or
For sorry?
for the setting they were considering?
Yeah. So for so I mean, I'm not a resource theorist. As it turns out, like later people came and told me this is a resource theory problem. We didn't approach it from system. We saw it completely geometrically. But in resource theory, they have these classes. Well, like with there's some free operations and what can you get from those free operations. And the resource class that the original papers considered was a much bigger class. And with this result, we sort of managed to collapse that class. We said, okay, this problem actually doesn't need to be in the larger class, it's in a much smaller class. That's the implication that I understand. But I see it from a much more practical point of view. I mean, you're saying that you want to recover pure states, but you're borrowing pure states while recovering pure state. Doesn't make much sense. So, from a practical point of view, this I think is the main the hard thing. Okay. More questions?
Yeah, it's science and
Yeah, unfortunately, it wasn't a chemistry talk, but I don't know whether it was much better than that.
distillation chemistry, purity,
Yeah.
catalyst chemistry, and short.